were calculator mistakes, calculator errors. And you gotta understand this, on these kind of a quiz, when you have your calculator, and I gave you the formula for even, I believe, for the input impedance to line, you have to be, when I give you the actual formula, then I expect you to be able to get the answer correctly. I'm going to give you one secret when you do these calculations in the calculator to help you. Run the calculations twice. It's called a redundancy check. If you get the same answers both times after you punch in the numbers, it's probably right. You probably didn't make a fat thumb error or something like this. But if you get different ones, then carefully check it. That's the general way to do it. All right. Yeah.
Did you say MathCAD is free?
MathCAD is free, one edition of it. Doesn't have the full functionality, but the one I use is free.
Okay.
And, did anybody else download it?
I was trying to download, I was just wondering.
It's called PTC, I think, MathCAD.
Okay, that's all.
And there's one edition that's free. If you want the fully functional one, it costs some money. And but I use this extensively for everything. All right. Now, does anybody have any questions about the quiz? Because it was meant to be a very straightforward. It was based on the problems that we outlined in class, I think twice. And I don't know. I think the highest grade was a 9. I didn't see a 10 on there, but it was meant to be a very straightforward kind of quiz. I don't know if we need to go through it. I suppose we can go through it one time. The solution's there, but why don't you get your calculators out and work with me before I get into snow charts so we make sure we know where the errors are. And I have a feeling some of you don't quite know how to use your calculators because I think you have the right formula down, the wrong number pops out, so I don't know what you're doing wrong. I'm just leveling with you. I can't tell you how to use your calculators because there's so many different ones, but I can tell you when your calculators are giving you the wrong answer. So for this problem, this is the quiz. Then we have the transmission line, then we have ZL, and we have Z naught, and we have the length L. And for this one, give me the specifics again for the voltage source.
Source voltage is 100 at an angle of 45.
And I'm going to do this, put it 100 e to the j pi over 4, if you want it that way. All right. RS is 50, isn't it?
Yep.
And Z naught is 50. And ZL?
60 plus 100J.
J100. And this is all ohms. And the length of the line?
1.3 meters.
And the frequency?
100 megahertz.
All right. C is 3 times 10 to the 8th. And the velocity on the line is C, right? So we're going to go through this problem and make sure you catch where you made the mistakes. Because it's real important a problem like this you can do without error, because this is like a building block kind of problem. So for this one, first thing I do is take this and I reduce it to plus to minus this voltage. I'm just going to label it as VS. We'll put the numbers in a second. Here's RS, and then here's my ZN. And I need this voltage, which I'm going to call V prime right there, or VN. So VN is equal to VS times ZN over ZN plus RS. Before I put the numbers in here, I have VS equals 100, either at an angle of 45 degrees or e to the j, 40 pi over 4. Now I need my ZN, and ZN is Z naught times ZL plus J, Z naught tangent of beta L over Z naught plus J ZL tangent of beta L. Here, beta is 2 pi over lambda. The length of the line is going to be in lambda is going to be equal to 1.3, right, divided by lambda, and it would be lambda. So now lambda is C over F. That's 3 times 10 to the 8th over 10 to the 8th, or 3 meters. Is everybody with me so far? I'm just pumping up. Did you all agree with this? All right, now, for this, therefore L in terms of lambda is 1.3 divided by 3, whatever that comes out to. And when I have beta L, that's 2 pi over lambda times length of the line in lambda, which is 1.3 divided by 3 lambda. So that's 2 pi times 1.3 divided by 3, and that's in radians. Can you give me that number? I just want to make sure we get this.
Uh, 2.72 radians.
Remember, that's radians, not degrees. All right, now, the next thing I want to get is tangent of beta L. What do you have for that?
Negative 0.447.
Would you all check and make sure you get that? Everybody? Now, I'm going to say one thing. This is what I'd store, this value, because you're going to, if that appears twice in that ZN formula. Do you follow me, class? All right, now, after that, tell me what Zn is. And of course, Z naught is 50. I'm not even going to put that in the equation because it's right there. Z naught is 50. ZL is 60 plus J100. What do you get for that? And give it to me in real and imaginary as well as polar. Please do it on your calculators. You'll thank me in the end. You're going to find out where you are making mistakes on your calculators. Nobody downloaded MathCAD on here? Yeah, you tried, but.
I tried, I just didn't know which one to get, but now I saw that one, I get it.
You'll thank me for it. There's tricks I can show you with MathCAD too.
Yeah, 49.99.
Hold on. So it's 50. Go ahead.
At an angle of 68.12.
1-2 degrees. And give that to me in real and imaginary too, because some people just give it to me in real and imaginary.
18.629.
18.629 plus
And then 46.389.
389 ohms. All right. How many got that, by the way? Did you get it? I believe that's the right answer. Their solutions are up there. Are you following me on this? People make mistakes on this. It's real important you get this through this part. All right, now if that's Zn, the next thing we have to get is Vs. That's Zn over Zn plus Rs, or it's 50 plus Zn at the denominator. Numerator is just Zn, or 50 at an angle of 68.12 degrees, times Vs, and Vs is 100 at 45 degrees, so that's Vn. Tell me what you get for Vn. And go ahead and give it to me in real and imaginary and in polar. And I want to find out where the problem is. I mean, if you got it right, just
It's 60.35 at an angle of 79.06.
79.06 degrees.
Yep, and then real is 11.45 plus J 59.25.
59.25?
Yeah, that's what I got.
25. I mean, volts. Are you all got that, class? Now this is the part people messed up. So that's Vn. Now what is Vn equal to? Remember, this is the zero marker, right? Here, Z is equal to minus L at this point where Vn is, right? So now we have to take the input voltage, which is V0 plus times, I mean, this is the voltage on the line anywhere, e to the minus j beta z plus reflection coefficient times e to the j beta z, and set it equal to Vn. And this is going to be at L, or really at Z equals minus L. We didn't get the reflection coefficient, we'll get that right now. Reflection coefficient is going to be ZL minus Z naught over ZL plus Z naught. Give that to me in polar and in Cartesian. Just real and imaginary. You can just read it.
0.676 at an angle of 42 degrees.
All right, and in real and imaginary?
0.5023 plus J 0.453.
Okay, so that's the reflection coefficient. Now we have that. You're gonna notice this. This is in degrees again. I would put everything in terms of radians if you're gonna do this calculation, because look at this. You gotta multiply this times this. This is EJ at an angle. Beta times Z is gonna be beta times L, which is gonna be in radians. Do you follow me? You have to make sure we've got the units consistent, and you have to do this operation correct. I recommend you work with radians, unless you really know what you're doing with degrees. So I have to calculate V0 plus, and Z here is gonna be at minus L, so therefore V0 plus is Vn divided by, and it would be e to the j beta L plus the reflection coefficient we just calculated times e to the minus j beta L. And realize the z becomes minus L, so this changes sign here and here. And so we get V0 plus. Please give that to me. Polar as well as Cartesian, real and imaginary.
The 6.22, oh, I'm sorry, no, 5.166 at an angle of negative 1.93.
5.166 at an angle of
Negative 1.93,
degrees?
radians.
Radians, okay. All right. And in degrees, it would be 5.166 at an angle of what?
Negative 110.9.
Minus 110.9 degrees. Did y'all get that, class? Please make sure you find your mistakes, because this stuff, it tends to just snowball. If you don't know, if these calculations you don't have considerable confidence in, then the next set, as we get down the line, you're gonna have a lot more trouble with, especially when we do impedance matching. You get it right?
I'm getting a different Vn for only the complex.
Wait, you're getting a different value of this?
Yeah, but only for the complex form. I have the same polar form.
Well, I'm gonna tell you, if that's right, then this to here should be an automatic. They both should be positive. What do you have for yours? Because this is almost 80 degrees, so the imaginary part's the majority. What do you have?
I have 16.05 plus 58.
It's 79.06 degrees?
Oh, it's 74 degrees.
All right, well, I'm gonna tell you, that means somewhere over here, is your Zn the same?
Yes.
And therefore, if your Zn is the same, then this calculation should give you that, unless, how many got this right here, what's on the board? All right, I could look up here. I'm not sure where, there's probably something you're not seeing, but it's probably something like a 4 that's put in as a 1 or something like that. You got this value? I mean, did you get this right here? Vn here or not? Did you get this?
I got it at 74 degrees.
So I'm gonna ask you one thing. You put Vs as 100 at 45 degrees in there?
Yes.
And you got a different value there, huh?
Yes.
Well, I'm gonna level with you. I'm not sure how that can happen. I'll just tell you. Ivan, did you get that?
Yeah, I got that.
You guys have the same calculator, you and Josh?
No, we're not using the same one.
What are you using?
This one? Just a scientific one that's complex.
got 79 degrees is for the angle, and 60.346 is the magnitude. So that's right, I'm not sure how come your answer is different, but we can take a look at it after class, how's that?
Okay.
All right, now, after that, did y'all get this for V0 plus? This is the one you didn't. I'll tell you what I got for V0 plus. For V0 plus, I got minus 17.918 minus 46.679. Is that what he has there? Oh. Hold on. This is
equals to 50 at negative 11, well, 111.
minus 17.918, and it's minus 46.679, and I think that's gonna be the right magnitude. The magnitude of the angle? I don't know the solution. Check that, you guys,
The magnitude is 50, not 5 points.
what's that?
The magnitude is 50, not 5.16.
Oh, my bad. I think, is it 51?
No, it's pretty much just 50.
Did you get this, Josh?
Yeah.
All right. The magnitude is 50, and at what angle?
Negative 111 degrees.
That's real and imaginative, that's out of mine. Y'all getting this or not? Right here. Remember for Vn, you have to put in, for V naught, you have to put in Vn, which is this value on top, and then divide it by that. It's important we get this stuff straightened out now. Because there's not a lot of partial credit when you have a formula in front of you for this stuff. And what I did was this. Possible 10 points, 10 out of 10. Each problem was worth 1 point, so I only took 1 point off. For if you missed all of them, you got a 5. I try to kind of proportionally scale upward. You getting this now, guys? Are you?
Yeah.
I encourage you to check your calculators and calculations, because this is where you can find out where you're making an error. Usually, it has to do with radians or degrees, or it has to do with dividing something incorrectly, where you're gonna, instead of adding this plus this and dividing it, and you're dividing this into that, and then this into that, and adding the results. There's stupid stuff like that that happens all the time. All right, you got it?
Was VL what we found,
Pardon me?
for the V naught plus equals VN over E to whatever, was VL,
What do you talk? Oh, beta L.
yeah,
Beta L is right here. It's 2.72 radians.
okay.
Okay? All right. We good? Now, after that, that's the voltage on the, that's V0 plus. And then when we want the voltage at the load, which is here, this is VL. The only thing we do is use this equation, now that we have V0 plus, and set Z equal to 0. Does everybody see that? So then, for V0, or for V load, the only thing it's going to be is going to be V0 plus this value times 1 plus gamma L. Because if Z is 0, the E to the J beta Z terms are just 1. Follow me, class? All right, now what do you get for the load voltage?
.7, an angle of negative 94 degrees.
Minus 94 degrees?
Yes.
Let's see what I got. 78.446 is what I got for the magnitude. Now, that's close enough. Do you guys get that angle, 94 degree, minus 94? Ivan,
Yeah.
you got it? All right. Let me do the last part here. So that's the voltage at the load. I asked for the current at the load, right? Once you have the voltage at the load, current at the load is just VL over ZL. That's it. And can you tell me what that is? I mean, there's no trick to this. It's VL divided by ZL.
0.673. At an angle of negative 153.30 amps.
Degrees, right?
Yes, degrees.
All right, and that's amps. Now, check it, make sure you do this right. You've got to be able to do a division like this right on your calculators. Are you looking at the solution instruction?
Yeah.
All right, it should have that value as far as magnitude. All right, then, if that's IL, the next thing I want is the power absorbed by the load. And that's simply 1/2 the real part of V, and I'm gonna put it in there. V at the load was 78.7, right? At an angle of minus 94 degrees. And it's times I conjugate. So the conjugate would change this sign to be a plus, so it's times 0.673 at an angle of 153 degrees. And remember, it's the real part. So for this, you're gonna have 1/2 times this, and the real part would be 153 minus 94, the cosine of that. So its final answer is 1/2 times 78.7 times 0.673, and then it's times the cosine of 153 minus 94, and this is in degrees though. And that should be P at the load. And I got that 13.575 watts. Y'all get that? All right. The big mistake that I keep saying is this here and ZN was wrong. Those are the two biggies that people seem to have trouble with. The P, this right here, I thought we went over this fairly, we went over this quite a bit. And I'm not, some people did have V and I right. I think you were one on it, but you got the power one, didn't you?
I got twice that. I forgot to divide by 2.
All right. It's important that you know these, and the way you get good at it, just working problems over and over. That way it'll stick with you. Don't try flashcards and memorize it because you don't link it to the actual solution. All right. Any other questions about this? Any questions? All right. Some of you are probably kicking yourself for dumb mistakes. And I understand that. All right, now on to Smith charts. The videos that I linked you to by that woman are excellent in my opinion. So what I'm gonna do is ask how many watched those videos? About half of you. If you get a chance, I encourage you to watch them. When I put them up there, it means please watch them. Take the time to watch them. It'll mean a lot to you, and will also save me some time in class so we can spend more time working problems. And that's a lot of times where you see theory worked out. We're gonna start, if you can get your Smith chart out and compass. And we're gonna start very simple. So the Smith chart really what it amounts to is a graphical representation of the normalized input impedance and the real and imaginary part of the reflection coefficient on a graph that will allow you to move either forward forward or backward along the transmission line and find both the reflection coefficient, the standing wave ratio, and all sorts of things, but it's an easy tool. So first with the Smith chart, what I like doing, or what I think we should do it, that is, I'm gonna draw it, just get one out, I'm not gonna move fast. I always like marking this center point right here, and then putting the R=1 circle right here. And I also do this, I show you that this is gonna be, the North Pole is plus J1, the South Pole is minus J1. And we're gonna actually go ahead and do some problems. This will sort of imprint on you how to do them. So you can have your notebooks out next to you, but now we're gonna go ahead and do a couple of things. You know that quiz problem we just did? What we're gonna do is this, we're gonna do the quiz problem in a sense. So we have a line with a characteristic impedance Z0, and it has a load here, ZL. Z0 was 50 ohms. ZL was 60 plus J, 100, right? And we have the length of the line in wavelengths. Now you always have to put the length in wavelengths. How long is the line wavelengths? The half wavelength, quarter wavelength, whatever. Here the length of the line was what? It was 1.3 over 3 lambda, right? And what's 1.3 over 3?
0.43 repeating.
0.43 lambda. Now keep that in mind. So, what we're going to do first of all is we're going to calculate the reflection coefficient using the Smith chart. So to get the reflection coefficient, what I need, and I'll do it, first I have to normalize the input impedance, so I take the ZL and I divide it by Z0. ZL is 60 plus J100 divided by Z0, which is 50, right? So here I'm going to get plus J2, and I have 6 over 5, or really 12 over 10, or 1.2 plus J.2. You all see that? Are you with me, everyone? Now follow me on this. Now we have to locate this point here. Here you're going to need to make sure you have, you've got to do this carefully. So for the 1.2, just watch this. I know this is the R=1 circle, right? All the circles that really are symmetric about the equator of this are real components, right? If this is 1.2, 1.12 is inside, just slightly inside here. See if you can find, and you're going to have to approximate this. It'll be just inside here, and this is going to be 1.2. Can you all see that? You see how if you get closer and closer, just look here. This is 1, this would be like 1.2, 1.4, 1.6. Do you all see that? Yeah. All right, find the trajectory that has the real part 1.2. It'll be just inside there. Do you see it? Now, the next thing you have to do is locate the J2. Now, here's how you do that. And I always use the J1 as a reference. The North Pole is a J=1, right? As you go this way, the values get larger. So J2 is about here. You're going to see, please just try to find it. This would be about J2. Can you all see that? It'll be right on the outer edge. Locate J1 and keep moving in. You're going to see J2. Do you see it? Allie, do you see this right here?
Yes, sir.
Y'all got it in the back? Ivan?
Yes, sir.
Andrew, do you see it or not?
Yeah.
You sure?
Yeah, that's right.
All right, now locate the point where the two intersect. This is the 1.2 and J2. And label that 1. That's point 1, and that's ZL. I always put a circle around it. So that's the first point. Follow me? Now take your straight edge and draw a line from the center here right through there. Just like that. And while you're at it, do this also. Take your compass and scribe a circle with a radius from the center point to the point where ZL is. So this would be the point you'd hold. Now please do this. You're going to see some variation, but this is real important what I'm showing you. We're going to get the reflection coefficient. If you don't see it, have a compass? Does anybody not have a compass here?
Just borrow this too.
Alright, you see this? Alright, you have this right circle there. And now, if you look out there, you're gonna see something. Alright, guys, you're gonna see something that says on the outer circle, wavelengths towards generator, WTG, and it'll be going this way, but you're also gonna see degrees. You're gonna have something that has something degrees here. Can you all see that? Yep.
Draw the circle from the point 1.2 or from the direct center.
You put the pin, or the point of the compass right in the center, and then you do this. You just take that out to here, and then basically make a circle.
Okay, I'll just make sure it's that point.
Yeah, it is. And you have a compass, here's what you're doing. You take it right here. Is that the right point?
Yeah.
And just make a circle. But I want you to take a look at this. This is the length of the line right here that's proportional. This is going to be the magnitude of gamma L right there, from here to here, and you're going to measure it down here in a second. I'll take you there. But first, look here and see where that straight edge of yours, or where that straight line, it penetrates the outer rings, and you're going to see one of those circles has degrees on it. Do you all see that? How many degrees is it?
42?
It's like 42, 43.
That's about right. Because remember, we actually calculated the reflection coefficient, right? It was 0.6 something, and it was at 42 degrees. Go ahead, look on each other's work. Please help each other. Did you get 42? All right, now, here's what you need to do now. Take your compass and measure the distance, or take it from here to here, and then take that distance and come down here. And you're gonna see something that's going to be indexed, and it's gonna be gamma. It's gonna be the reflection coefficient. You all see that, class? Let me try to show you here. The reflection coefficient, ERI, of the black magic is at the it's just above the bottom. So the way you measure it, now some of these may be different, but I want to tell you, if you look at this, you're going to see something that says REF and then coefficient, COEF. You all see that? Now it's at the very bottom of the page. You put your compass point from here, and you move this thing to the distance that this was. So this would be gamma L, magnitude. And you should be able to read that off. You all see that?
Yeah.
All right, what do you get for that?
0.68.
0.68? 0.68, and we got an angle of 42 degrees. Now, what did we have in the quiz for the actual reflection coefficient? Do you remember?
0.676.
At an angle of?
42.02.
All right, so it's close. And I'm going to tell you, your eye and the sharpness of your pencil and the steadiness of your hand is where the error is. All right. These are all small errors, but this is a much quicker way to do this problem using a Smith chart. You won't believe how fast it is. So now I've got the reflection coefficient. Now, I needed to calculate Z in, right? That was the next one. So now we're going to calculate Z in. Write that down. And to calculate Z in, what I have to do is this. And I want you to watch this carefully. We'll make sure everybody's looking. Do you see it, Andrew? Mm-hmm. Well, the reflection coefficient, I want to make sure you do it. It's right down here. Oh, it's over here on yours?
Yeah. So it's
Here. All right. It should be, wherever it says 0. Pull that up and make sure you can see that it is about 0.68. Okay. Now, here's the next thing. Y'all got that, guys? You see it?
How's it be the angle?
The angle is right here. If you look at the where this line pierces this, there's going to be one is wavelengths towards generator, then wavelengths towards load,
Okay.
and then angle.
Alright.
And actually, you can measure that if you have one of these what do you call those things? The arches with the angular degrees on them. Yeah, that'll do it. Protractor would. You don't even need to use that, but it's much easier to use that. Got it? Yeah.
Where's the coefficient on here?
All right. On yours, if you look here, if you look here, you're gonna see, when these change, you're gonna see reflection, right? Reflection coefficient here. So what you do is this, you start here, and you put yours right here. You see how it's about 0.68? But they will vary on some Smith charts, location of those things. I don't want to tell you what the reflection coefficient magnitude really is. When I talk about the reflection coefficient magnitude, listen to me now. What it really is a ratio. It's simply the proportional ratio of the length to ZL compared to the length to the outer rim. That's all it is. So the closer this gets to the outer rim, the closer the reflection coefficient gets to 1. And the closer it gets to the center, the better it is. It's going to 0. Follow me? You would like a reflection coefficient of 0. Follow me on this, class? That's what it is. Now, the next thing we're going to do is get Zn. And the way we get Zn is this. I want you to watch this because this is important. Locate on the outer part of your circle WTG. It means wavelengths towards generator. Now we are at the load, so the only way we can move is towards the generator. Does that make sense to everybody? So find the outer part, WTG. Now the next thing you do, and please work with me on this, and I don't want to fly through this, I want to make sure everybody sees this. There's a thing I call a mile marker, but there's something that's going to say, and I'll just tell you how this works. Here, right here is 0. As we go this way, it increases and it increases. You're going to have something that goes 0.25 here. This is 0 on the outer part, wavelengths towards generator. Do you all see that where it's 0?
Yeah.
And you all see this is 0.25. Take a look at that.
Yeah.
Now, anywhere between here, it's something between 0 and 0.25. And the closer we get to that, the closer it is to 0.25. Now here, when I look here, I should have a number of about 0.21, something like that. On the outer circle, what do you have?
0.19.
Yeah, 1
All right, 0.19 lambda. It is in wavelengths, so write that down, lambda. It's not meters, it's wavelengths. Now listen, now what we have to do, we're going to keep moving wavelengths towards generator. There's our starting point. Think of it as like mile marker 25 on a highway. Now we're going to add that many more miles to it. In this case, we're going to add 0.43 lambda, all right? We have 0.19 lambda. We're going to add 0.43 lambda. So do this with me. We're going to move from here. We're going to move all the way around to, and this is 0.43, but there's a secret here I want to show you. When I have 0.19 lambda, right? 0.19 lambda, that's where I started. I'm going to add 0.43, right? Lambda to it. So it's 0.62 lambda. Do you see that? Now I want you, this is the mile marker I started at, and I'm adding the length of the line to it. And this is where we're going to end up. Now please watch this. This is very important because people get confused right here. Now you all see that whenever I come through this point, I start at 0 again. Do you all see that? Why is that? From here to here, it's a quarter of a wavelength. From here to here, it's a quarter of a wavelength. And what this means is every half wavelength, whatever I'm doing repeats itself. And this is true with the transmission line. From here to a half wavelength, there's a unique value for everything. But every other half wavelength just repeats those values, if you can appreciate what I'm trying to say. Now, so how do we deal with that? Anytime we get a value greater than 0.5 or less than minus 0.5, we either subtract or add half a wavelength to bring it back closer to 0. In other words, for this, I'm going to subtract 0.5 lambda. It doesn't do a thing if you cut off a section, if you're half wavelength sections, right? And when I do that, I get 0.12 lambda. Do you all see that? Now, why did I do that? Because this now is what I call the mile marker. It's the point wavelengths towards generators. So when I go around here, I go around, and at this point, please find this. You're going to see 0.12 lambda. And the only thing I did is I moved from here all the way around 0.43 lambda. I've added to this point. In order to find the mile marker, I have to subtract the 0.5 because at this point, I'm going through the 0 point. I have to subtract that. Can you all see that 0.12 lambda?
Mm-hmm.
Want to make sure everybody can. You see it? Duncan, do you see it?
So like towards the top.
Yeah. Josh, you got it? Alan, do you see it? All right, everybody? Now, take your marker. It's about here, isn't it, class? Or actually,
J1.
it is actually before. You're right. It's right about here, isn't it?
Yep.
All right, now draw a straight line through there to the center point of your circle. It's not a straight line. Try that again. Right? And this is 0.12. Okay? Now we're going to get the input impedance. You can do this like that once you do a couple of these. Now mark that point. This is 0.1. We're going to move this way. We're moving 0.43 lambda. And now this is going to be 0.2. And label that the normalized Z in value. So when I look at that, I can say the normalized Z in value would be equal to, and now you've got to read this, so I'm going to show you what it should be about. Now remember, this is the R equal 1 circle, right? As this circle gets bigger, R goes down. So here, I'm going to get a value of R of like 0.5 or something. Can you see that? Just take a look at the circle that's symmetric about the equator, and tell me what that value is for R.
0.36.
So it's R equals 0.36, is that right, anybody? Now, for the imaginary part, you're also gonna have this. You're gonna have something that shoots through here, and you're gonna see whatever that arc is, this trajectory that's closest to it, you're gonna have J of what?
0.88.
0.88, right here. Are you getting that, guys?
Where's the 3.6, like 0.36?
All right, can you see circles that go from here that come right through this point? Like if you start here, you're gonna see one that, I'm trying to show you, but you all see it? Please make sure you see this. This is real important.
Yeah.
Now, and so you should get the value of Zn as 0.36, approximately 0.36 plus J of 0.88, did you say, or 86?
0.88.
Did you all get that, class? It helps to use a sharp pencil, and if you can buy like a compass, she has, these kind of really good. This is a drafting compass. These things don't wobble and stuff like this, so you get fairly precise measurements. When you're doing it, it pays to have that. Now that's Zn normalized, right? When I say normalized, it means it's the value divided by Z0. To get actual Zn, we simply take Z0 times small zn, right? And since that's equal to 0.5, right? Zn is 50 ohms. If you take 50 times that, what do you get?
Plus 44
And what did we get for our input impedance before?
18.6 plus J46.
46, all right, we're a little off. Can somebody else check that, see if, is this right, 0.36? We're probably making errors of the eyeball, and it's still pretty close. You'd be amazing how close it gets when you use a sharp pencil and a large one. Did you get this value, Josh, in yours?
I mean, it was close.
Yeah.
Help me out.
0.375.
Yeah, that sounds better. That's right. Plus J,
0.925.
that's 0.925.
Yes.
All right, now try that one and see what you get. Because he has a bigger Smith chart. He has the ones I handed out, the really large ones. Are you using Black Magic or which one are you using?
The Black Magic one.
Yeah, that's smaller as far as it, so you're gonna introduce more error. What did you get? I think it's smaller at least, maybe not. Can you multiply that out for me? 0.375 plus J 0.925?
18.75 plus J 46.25.
And our actual values were what?
18.62 or 63 and J46.
You see how close they are? And that's why if I'm doing precise calculations, I'm gonna just grab this one. Use this large Smith chart, just make copies of that I handed out, because that's the good one. It's blown up. I think that's full size. Yeah. Now here's the Black Magic is a little more condensed. I suppose you could enlarge that and get away with it, but I'm just telling you that one, Dr. Wentworth found that one time and we made a whole bunch of copies. That's actually the ones that they use back in the day, I think they're the ones they used with Hewlett-Packard and stuff like this. If you did real work, you get thick piles of these that you started with, and you put you put your number, project number in the corner and stuff like this, and you worked them and you labeled all the points so they saw what you do. All right, now that's Z in. Now I'm going to show you some more. This is stuff that I haven't got to yet, but there's a standing wave ratio. Write this down. I didn't mention this, didn't I? I said the standing wave ratio was equal to 1 plus the reflection coefficient of the load's magnitude over 1 minus the reflection coefficient of the load's magnitude, correct? Y'all remember that class?
Is that the VSWR?
Yeah, it's standing wave ratio. It could be VSWR or ISWR.
Yeah.
But it is the voltage standing wave ratio or the current standing wave ratio. They're the same thing, but it's called the standing wave ratio. That's the form of calculation. And we can do that, right? You can just do this. Remember, it's a magnitude, so it's actually 1.68 here, because the reflection coefficient is 0.68, and then it's 1 minus 0.68 here. So you're gonna just get a standing wave ratio of, what is that, 0.34. So it's 1.68 over 0.34, and I don't know what that is, but 5 maybe?
5.25.
5.25. But here's how you get it on a Smith chart, without any calculation or an approximation. I want to make sure I got everybody's attention. To get the standing wave ratio, remember that initial arc you put on here, that circle? Right? Where the circle crosses the equator between the origin and 0.25, you're going to read a number, and that is the standing wave ratio. Go ahead and take a look at that right there. It's going to be a number, and you're going to see the value be about 0.52. Can you see it? Remember, you're on that arch you actually drew with the magnitude of gamma L. The first circle you drew. You all see it? Are you getting about 0.52? It's 0.525. If you can see 0.525, then you're a better person than me. I can't see that far down. Y'all got that on there? What's wrong?
I'll just do a little bigger.
Well,
Here's
That's right. If you look, no, don't worry. If you look right here, you got it. This is right here. See, this is 0.25. That's 0, right? Look right there. Isn't that about 0.525? That's 0. That's 1.2, 1.4. The load. It goes to 0.5 right there. So it's 0.525. You see? There's 0.5, or 5. I mean. So that's the standing wave ratio. Now, something else I'm going to tell you. Whenever you talk about the voltage on the line, now listen to this, it's important. Whenever you talk about the voltage on the line, we know our load was located, or when we came into the Smith chart, we were here, right? When I move from here to this point, right here, this is where Vmax occurs. This is going to be the maximum voltage will occur this distance away from here to here. Let's find out where that distance is. If I asked you a question, this is a legitimate question. If I asked you where the voltage would be a maximum, we could do it with equations. I promise you we can do it. But it's much easier to do this. I want to know how far from here I have to go before I get this, standing wave ratio would hit a maximum right there, the voltage, and then on the line and hit a minimum and stuff like that. So how far do I have to go? See this 0.19 lambda? That's where we entered. This is 0.25 lambda. Follow me? How far did I travel in terms of lambda? I went from 0.25 lambda minus that mile marker, 0.19 lambda, and that's going to be 0.1? 0.06 lambda. So when I go 0.06 lambda away from this end, I'm going to hit a Vmax. Okay? Now, wherever the maximum voltage is, so that's where Vmax is, it's going to be 0.06 lambda away. When you go a quarter wavelength from there, this segment would be 0.25 lambda, then you hit Vmin. And here's what happens. If I'm right here, think about this, I'm like moving around or moving down the transmission line. I come here, I hit a maximum, you following? I'm at the load, right here. I come down, I hit the maximum value of voltage. Then I keep moving. When I move a quarter wavelength, this is my Vmin. That will be the minimum value of voltage. Are you with me? And the minimum value of voltage is just going to be 1 minus the magnitude of the reflection coefficient times V0. The maximum voltage will be 1 plus the magnitude of the reflection coefficient. So I want you to know something. Vmax right here, Vmax, and this is the magnitude, is going to be V0 plus times 1 plus the magnitude of the reflection coefficient. And Vmin, magnitude, is going to be V0 plus times 1 minus the magnitude of the reflection coefficient. With me, guys?
Where exactly is the Vmax again?
Maximum value is going to be, it occurs, it's actually how far you move. This is the 0.19 lambda. This is where I came in, right? Mm-hmm. I have to move down, down, down until I hit 0.25 lambda, right here?
Yeah.
And how far is that? Well, I went from 0.19 lambda to 0.25 lambda, so that's going to be 0.06 lambda. So when I go down the line 0.06 lambda, I know I hit Vmax, and if I add a quarter wave to that, then I hit Vmin. And if I had another quarter wave, now I'm back here, and the thing repeats itself. You got me on this? So, again, to recap, the way you use a Smith chart, first, you normalize the input impedance, and you find Z load normalized. Then from there, you can get the reflection coefficients, magnitude and angle, and you always take a marker on the wavelengths towards generator point out there. Then you move as far as you need to in terms of wavelengths to get to the input. At that point, you go and relocate on this circle, that the initial circle you drew, and I should have said this, that you're gonna take it and draw a circle from the origin to the actual point, ZL, and circumscribe that circle, and then you're going to be moving wavelengths towards generator in the clockwise direction until you've hit, you're always going to add values to the wavelengths towards generator initial number to get to as many wavelengths as you need to go towards the actual load. And then when you land there, the only thing you have to do is multiply it by Z0, you have Zn. You can get the standing wave ratio there. You can get the actual distance to the maximum from here to here. And practically speaking, that sort of is the problem we did, right? I mean, we didn't get V0 plus there because once we have the input impedance at this point, right here, then we can get the input value of Vn prime, right? By using Vs times Zn over Zn plus Rs, and we can get it, we can solve the problem. So that's the beginnings of impedance matching. This is the beginnings of using a Smith chart. Now, there are going to be several problems I'm going to assign to you. I'm going to ask you to do them. I'll give you the answers, but what I'd like you to do is struggle through without looking at the answers first. Then use the answers to confirm it. Now, I'm going to level with you guys. This takes some time and discipline because you're going to see you'll have questions come up that I haven't addressed and that I don't see coming. So remember that. There's going to be some questions. This is it. This is basically how to use this to calculate the impedance. Let's go in reverse and try something. Suppose instead of that, let me get a clear slate. We're going to do the inverse problem. So now here's the problem. I generally encourage people to draw this out until you get till it's second nature. Here's ZL. Here's Z naught. All right. I'm going to give a length of line L equals 0.2 lambda. And I'm going to say here I have Zn equal to say 50 plus J 30. All right, so I'm giving you the input impedance. I'm not giving you ZL. And I'm going to say the characteristic impedance is going to be 100 ohms. So here's my question. First question is, I want to know the value of ZL. Are you with me? Now we could get it from an equation. We could write Zn is equal to Z naught times ZL plus J Z naught tangent of beta L over Z naught plus J ZL tangent of beta L. We could manipulate that. It would take a while, by the way. It's not easy.
Is that Zn?
This is Zn right here. Zn. Now, how do we do this problem? First, if you can, get a fresh Smith chart out to do this one. How do we do this problem? And you'll see there are many permutations of this. This is 0. This is 0.25. This is the center. I always draw the article 1 circle if I'm freehanding. This is J1. This is minus J1. And now, this is article 1. So I have Zn equals 50 plus J30, right? And I know Z naught is 100. Y'all with me? Matter of fact, let me do something. Let me just make this 50 instead of 100. It'll make it easier. It'll be easier to read. So now, what is the normalized value of Zn? That would be what?
1 plus
50 plus J30, you're right, Duncan, but over 50. So it's going to be 1 plus J 0.6, right? Is that right? So locate that point. So 1 is here, right? That's this circle. And J.6 is about here. This is, well, maybe further out a little bit, but this is J 0.6. Can you all see that? And locate that point right here. This is going to be 1 plus J 0.6. And that is Zn. Y'all see that, guys? Now, once you locate that, take your compass This is the inverse problem. We're going from where we ended, and we have to go the other direction to where we began. Now draw a circle from here, the center point to this, right here, and draw it around here. And the radius of this circle right here is the magnitude of the reflection coefficient. Remember that. Can you all see this? I know it's a little tight, but that's why a good compass helps a lot, like the one she has, and a large Smith chart like the one Josh has. Ivan, you got a good compass too, don't you? Are you using a big Smith chart or not?
Even the big one, yeah, the one that you provided.
This is a little tougher to read.
Not like the same as your class.
Well, the real part is here, right? R1 is just this circle, right? The J part is J.6 is right about here, isn't it? Maybe it's further out, a little further out, something like that. You all see
Yeah,
that?
I've got that one.
And then look where the trajectories intersect, all right? It should be about here. Y'all get that?
Yeah.
Now take your compass from here, center point to that point, and put a circle there, right? And then take your straight edge and shoot it out here. Where did you get that point, Josh? Oh, you're not? Are you doing that one or not? No.
Yeah, I don't have a compass though.
Oh, well, isn't the point up here?
The point,
Oh, there we go.
and then we,
Yeah, sorry, I couldn't even see it. Yeah, so why don't you let him borrow your compass when you're done? Go ahead. You guys got that? Now look, now we're at the load. We're at the load in, excuse me, we're at the, whatchamacallit, source in, right? The generator in. This is where the generator is, down this way. We want to go towards the load. So now you look there and there's a circle. The outer one is wavelengths towards generator. The next one in is called wavelengths towards load. Do you see it? WTL, there's wavelengths towards generators, the outer part, then there's wavelengths towards load. Do you all see it? We could use wavelengths towards it. There, it really doesn't matter which one you use, but here you look at the mile marker. What do you have there? 0.1.
3, yeah, or 3.5.
Wait. I've got 1 plus J.6 right there, correct?
Yeah.
All right, now listen to me. That's 0, and that's 0.25, right? But when it's wavelengths towards load, what's the value out here?
0.
It's still 0. So this has to be between 0 and 0.25, doesn't it? What's the value up here?
Goes the other way around.
Yeah.
All right,
It starts at 5.
So the negative half of the circle is 0 to 0.25, because it goes the other way around.
all right. What's the value again? 0.
It's gonna-
0.35, like 2.
Yeah. 3.1, something like that. Yeah, because the 0.
That's right.
0.25 on the bottom.
0.351 Bob, right? 351 lambda, right? Now you're gonna look, this is the way it increases this way, see?
Yeah.
Then you're gonna add to it the length of the line, which is 0.2. So when I take 0.351 lambda plus 0.20 lambda, I get 0.551 lambda, correct?
Correct.
It's not on there. What do I have to do? Subtract 0.5. So I subtract 0.5 lambda from there, and I got 0.051 lambda, correct? Right?
Yeah.
0.051 lambda is here roughly. Look at it. it's about here. 0.051 lambda. You all see that? You see it? Draw a straight line from the center through there. And just note this, this is actually 0.1. Now our trajectory goes this way. We're moving to this point, and this point right here will now be 0.2, and that is the normalized value of Z load. We came in at Zn, now we're moving towards the load. You follow me? What do you get for ZL here? You saw?
0.6 and 0.2 J.